Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of the mid-18th century hummed with a peculiar energy, an electrical enthusiasm that permeated salons and laboratories from Paris to Philadelphia. Within this charged atmosphere, the 1,747 correspondence initiated by Benjamin Franklin, later compiled and published as Observations and Experiments on Electricity, represents a monument of empirical reasoning and theoretical synthesis. This essay undertakes a direct and systematic evaluation of the core claims advanced within Franklin's foundational electrical writings, moving sequentially through the work's principal arguments from the initial formulation of a new electrical theory to its ultimate, spectacular meteorological application. We will assess the internal logic, methodological rigor, and conceptual power of Franklin's claims as he presented them. The purpose is to map the architecture of his thought, examining the evidence immuttled and to precise mechanisms proposed, thereby illuminating the profound originality of a mind engaging with one of nature's most fugitive and captivating forms. Section 1: The unified electrical fluid and the principle of conservation. Franklin's initial letters to his London correspondent, Peter Collinson, articulate the central axiom of his entire electrical system. He posits the existence of a single, subtle, and pervasive electrical fluid, a substance he terms electrical fire, which exists in a state of equilibrium within all matter in its natural, uncharged state. The genius of this initial claim resides in its elegant reframing of electrical phenomena. Charging an object, in his view, is the process of altering this equilibrium. An object with a surplus of this fire becomes what he designates as positively charged, or in his algebraic shorthand, plus. Conversely, an object from which electrical fire has been removed possesses a deficit and is thus negatively charged, or minus. This conceptual scheme immediately redefines the act of electrification as an act of transference, a displacement of the electrical fire from one body to the evaluation of this claim reveals its immense explanatory power. It accounts for repulsion and attraction with a beautiful symmetry. Two bodies in a state of surplus, both positive, will repel each other, as will two in a state of deficit, both negative. A body with a surplus and one with a deficit will, however, attract each other, in what Franklin conceptualizes as a powerful tendency for the electrical fire to restore its own equilibrium across the system. The crucial corollary to this claim, and perhaps its most profound contribution, is the principle of the conservation of charge. If electrification is merely the moving of a fixed quantity of electrical fire, then the total amount of this fire in any isolated system must remain constant. When one rubs a glass tube with a silk cloth, the tube accumulates a surplus of fire, becoming positive, while the cloth acquires an exactly corresponding deficit, becoming negative. The fire is separated, creating two distinct electrical states, yet the total sum of charge is unchanged. This idea, presented with the clarity of a balanced ledger, provided a quantitative and foundational law for a field previously characterized by a collection of qualitative and often puzzling observations. The evidence Franklin supplied was based on simple, repeatable experiments where the charging of one object could be shown to induce an opposite state in the object it interacted with, a logical and empirical coherence that lent his single fluid model immediate credibility and analytical strength. Section 2: The action of points and atmospheric discharge flowing directly from his primary theory is Franklin's analysis of the peculiar behavior of pointed conductors. He observed, with characteristic acuity, that a sharp metallic point brought near a charged sphere would silently and efficiently draw off its electrical fire, neutralizing it far more effectively than a blunt object would. His explanation for this phenomenon is a direct application of his single fluid model. He argued that the electrical fire, where accumulated on a conductor, distributes itself over the surface. On a sharp point, this fluid becomes highly concentrated, creating an intense pressure that facilitates its discharge into the surrounding air or its transfer to a nearby body. He likewise claimed the inverse was true. A grounded point could effectively draw the electrical fire from a charged object nearby, a kind of electrical siphoning. Critically assessing this claim highlights Franklin's talent for connecting a specific, observable effect to a general theoretical principle, the mechanism he proposed. A concentration of force at a sharp termination was a powerful and intuitive concept. He described points as having the ability to both throw off and draw in the electrical fire, making them active conduits in any electrical system. This was a crucial observation, one that moved his work from the purely descriptive to the predictive and utilitarian. The evidence was demonstrative. He constructed devices like the electrical spider, a small wire effigy, that would spin when its pointed legs discharged electricity, providing a visible and compelling demonstration of the electrical wind or current of particles being thrown from the points. This analysis of pointed conductors was more than a mere curiosity. It formed the essential bridge between his laboratory experiments and his grander atmospheric hypotheses. It suggested that a force that could be managed and directed on a small scale with a sewing needle might also be manageable on the large scale of a thunderstorm, a conceptual leap of immense audacity and consequence. His framework transformed the point from a simple geometric shape into a tool of electrical manipulation. Section 3. The anatomical deconstruction of the Leyden jar. Franklin's investigation into the Leyden jar, the celebrated electrical condenser of the age, stands as a masterwork of experimental dissection and logical deduction. The device, a glass jar partially coated inside and out with metal foil, was known to store a potent electrical charge, delivering a severe shock to those who completed a circuit through their body. The prevailing assumption was that the electrical fire was stored within the water or the metal conductor inside the jar. Franklin's claims methodically dismantled this notion. His procedure was an exercise in systematic elimination. He charged a jar, then, using insulating wax handles. He removed the central conducting wire and tested it held little charge. He then poured the charged water into a separate, uncharged jar and tested it. The water was also largely neutral. The astonishment came when he refilled the original jar with fresh, uncharged water. The jar was found to be still powerfully charged. The inescapable conclusion, and Franklin's central claim in this section, was that the electrical charge resided not in the conductor but was stored on the surfaces of the glass dielectric itself. His single fluid theory provided the perfect framework for this startling discovery. He explained that the charging process pumped electrical fire onto the inner surface of the jar, creating a positive state. This surplus on the inside repelled the natural electrical fire present in the outer foil, driving it away into the ground and leaving the outer surface with a corresponding deficit or negative state. The charge was thus a state of violent tension held across the non-conducting glass, with the surplus on the inside surface bound by the deficit on the outside. The shock occurred when a conducting path, such as a person's arms, allowed the surplus fire to rush across and neutralize the deficit, restoring equilibrium with startling force. This explanation was a triumph of his model. It accounted for every aspect of the jar's behavior with an elegance and completeness that competing theories lacked. It perfectly illustrated the conservation of charge, as the positive interior and negative exterior represented a separated but balanced quantity of electrical fire. Franklin's analysis transformed the Leyden jar from a magical box into a comprehensible physical system. Section 4. The electrical nature of lightning and the argument from analogy. Perhaps the most famous of Franklin's contributions is his hypothesis concerning the identity of lightning and laboratory electricity. Before undertaking any direct experiment, he constructed his argument in a purely logical and analogical fashion, a testament to his powers of observation and reason. In his letters, He presented a systematic list of 12 distinct properties shared by both phenomena. This list forms the core of his claim. He noted that both gave off light of a similar colour and crooked form, both were swift in motion, both were conducted by metals, both could inflame combustible materials, both had a characteristic sulphurous smell. What we now recognise as ozone, both could render metal magnetic or reverse its polarity. The evaluation of this claim hinges on the strength of his analogical reasoning. Each point of comparison, taken alone, might be circumstantial. However, the cumulative weight of the 12 similarities created a persuasive and compelling case. Franklin was building a probabilistic argument of such strength that it approached a logical proof. He was asserting that if two phenomena share a comprehensive and specific set of properties, it is overwhelmingly probable that they are manifestations of the same underlying cause. This was a sophisticated deployment of inductive reasoning. He was arguing that the difference between a spark from a Leyden jar and a bolt of lightning was a matter of scale, not of kind. One was the work of man in a laboratory, the other the work of nature and gay. Yet the fundamental electrical fire with this claim, presented before the famous kite experiment, was a theoretical proposition of the highest order. It was a hypothesis grounded in meticulous observation and structured as a formal argument, inviting experimental verification. Its power lay in its ability to domesticate a terrifying and seemingly supernatural force, bringing the thunderbolt of Jupiter into the realm of natural philosophy and empirical science. Section 5. The practical invention of the lightning rod. The invention of the lightning rod is the ultimate instantiation of Franklin's scientific method, where theoretical insight leads directly to a practical, world-altering application. The claim here is twofold. First, that a pointed metallic rod, erected on the highest point of a building and connected to the ground, could protect the structure from a lightning strike. Second, a mechanism by which it did so was a direct consequence of his previously established principles. The rod's primary function, as Franklin conceived it, was preventative. Building upon his claim about the action of points, he argued that the sharp tip of the rod would silently and continuously draw the electrical fire from a passing charged cloud, neutralizing the cloud's charge, and thereby reducing the likelihood of a violent strike in the first place. This was a subtle and elegant idea, suggesting a way to disarm the storm before it could unleash its full power. The secondary function, which has become its more commonly understood purpose, was to provide a safe and direct path to the ground for the electrical charge if a strike did occur. By being the highest and most conductive point, the rod would intercept the lightning, and the conducting wire would guide the immense quantity of electrical fire harmlessly into the earth, preserving the building itself from damage. This invention was a direct and logical outcome of his entire theoretical system. It depended on the identity of lightning and electricity, the conductive properties of metals, and most specifically, the powerful discharging action of points. Evaluating this claim requires recognizing its status as applied science. Franklin was so confident in the internal coherence and predictive power of his model that he proposed a public works project based upon it. The lightning rod was more than an invention, it was a physical manifestation of his theory, a silent, iron sentinel that stood as a testament to the idea that understanding nature was the first step toward living in harmony with its more formidable powers. Its eventual widespread adoption provided the ultimate, pragmatic validation of his entire chain of reasoning. Section 6. Confrontation with alternative frameworks and theoretical refinement. The publication and dissemination of Franklin's letters throughout Europe inevitably brought his ideas into dialogue with established electrical theories, most notably the two-fluid theory championed by the French physicist Béjin Nolet. An evaluation of Franklin's work is incomplete without considering the resilience of his claims when faced with this prominent alternative. Nolet's model posited two distinct types of electrical fluid, a vitreous fluid and a resinous fluid. Attraction and repulsion were explained by the interactions between these two fluids. Franklin's single fluid model, or Franklinism as it came to be known, offered a more parsimonious explanation, is framework, requiring only one fluid in states of surplus or deficit, represented a more economical conceptual tool, an application of Occam's razor to the field of electricity. The critical test for both models came in their ability to explain the behavior of the Leyden jar, Franklin's single fluid, conservation-based explanation, detailing the tension across the glass dielectric between an internal surplus and an external deficit, was clear, coherent, and accounted for all aspects of the phenomenon. Nollet's theory of affluent and effluent streams of his two fluids struggled to provide an equally comprehensive or intuitive mechanism for the jar's ability to store charge. The debate that ensued, carried out in publications across Europe, served to harden and refine Franklin's claims. It forced him and his proponents to articulate the logical superiority of their model in explaining the full range of observed phenomena. The success of the Franklinist model, particularly in England and Germany, was a testament to its internal consistency and its greater explanatory scope. This intellectual contest reveals the robustness of his initial insights. His claims were not merely clever observations, they formed a cohesive and resilient theoretical structure capable of withstanding critical scrutiny and providing a more powerful and unified account of electricity than any competing framework of the period. In conclusion, a close evaluation of the claims within Benjamin Franklin's observations and experiments on electricity reveals it as a foundational text built upon a remarkably coherent and powerful conceptual architecture. The work's enduring significance derives from its systematic progression of thought. From the initial, revolutionary claim of a single, conserved electrical fluid, Franklin logically derived a series of subsequent claims, each building upon the last. The action of points emerged as a natural consequence of the fluid's behavior, which in turn provided the key to both understanding the Leyden jar and proposing a method for taming lightning. Each step of his argument was supported by simple, repeatable experiments and a clear, almost literary, descriptive force. He bequeathed to the study of electricity a new and potent vocabulary, positive and negative, charge and discharge, and a foundational law in the conservation of charge. The work is a paragon of the Enlightenment mind, demonstrating a profound faith in empirical evidence, logical deduction, and the ultimate comprehensibility of the natural world. Franklin began by observing the sparks from a humble glass tube and concluded by explaining the thunderbolts from the heavens, a journey of intellect that affirmed the power of human reason to illuminate even the most daunting of nature's mysteries.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.